Welcome back to the STEAM universe, Cadet. I'm Professor L, your head mentor right here at the Academy. Today's explainer is actually a super special mission. We're diving right into the microscopic, neon-glowing world of electronic circuits. We're stepping inside the futuristic technology command center today, and we're going to learn exactly how the components that power everything, from your basic alarm systems all the way up to spaceships, how they actually work.
Oh wait, incoming transmission. Are you ready to accept the challenge and become a real-life circuit detective? Look, today we are going to make your GEC 2026 Worksheet 3A so incredibly easy that you'll literally finish it without breaking a sweat. Because instead of just memorizing boring textbook definitions, we're going to visualize all this data in a completely new, really fun way. Okay, let's dive right into our main objective for this explainer. I want you to imagine that every single electronic circuit is actually a superhero team. Seriously, every tiny component has a really vital, super-specific job. And, just like any great team out there, if one member fails or goes missing, the whole system just stops working. By the time we finish this mission, you'll know exactly what each and every hero does.
All right, let's jump in. Section 1, Controllers and Directors, Guiding the Energy.
First up, meet Captain Switch. You can't miss him. He's glowing in his signature electric blue. Now, his job is simple, but absolutely crucial. He basically opens and closes the circuit, exactly like a door. When Captain Switch opens that door, there's a huge gap, meaning no electricity can flow. But when he closes the door, boom, the energy rushes right through to power up the whole system. Next up is Diana Diode. See her bright orange glow and that cool arrow-shaped symbol? Well, Diana has one totally unbreakable rule. Traffic moves one way only. Electricity can enter from her anode side, sure, but she acts just like a strict one-way street. That electrical current can never, ever travel backwards on her watch. And right next to her is Lily LED, shining in radiant yellow. So Lily is actually Diana's cousin. She also acts as a one-way street for electricity, just like Diana. But Lily has this really special superpower. She glows. Basically, whenever electricity successfully passes through her, she converts that electrical energy straight into light. That's exactly why LEDs are the glowing indicators you see on your TVs, your phones, and of course, your alarm systems.
Now, let's actually compare these two directly, side by side. This is something that honestly tricks a lot of junior engineers. Over on the left, Diana Diode is kind of an invisible worker, right? She directs traffic in the dark. But on the right, Lily LED does the exact same one-way job, except she emits light while doing it. So the absolute crucial point to remember here is every LED is a diode, but not every diode is an LED. Make sense?
Moving right along to Section 2, Resistors and Sensors, Reacting to the World.
Say a big hello to Robbie Resistor, glowing in warning red. So sometimes electricity gets just a bit too excited, It wants to move way too fast, which can totally damage our delicate circuits. Well, Robbie acts exactly like a speed bump on a road. He doesn't stop the flow completely, he just limits it and slows that current down to a nice, safe speed. Now meet the green glowing Larry LDR. LDR actually stands for Light Dependent Resistor. Larry's superpower is literally tied to the sun. He changes his resistance based purely on light, so when it's totally dark out, he acts like a huge speed bump. But when bright light hits him, his resistance drops way down, and he lets so much more electrical current rush right through. And hanging out right beside him is crimson Theo thermistor. Now Theo changes his resistance based on heat. For our specific missions here, Theo is what we call an NTC, or negative temperature coefficient thermistor. I know, that sounds super complicated, but it honestly just means they move in opposite directions. So when the temperature goes up, Theo's resistance goes down. Simple as that. All right, here is your ultimate cheat sheet for environmental sensors. Take a look. On the left, the LDR is your light detective. Remember, more light equals less resistance. And on the right, the thermistor is your heat detective. So more heat equals less resistance. Really recognizing these specific triggers is basically the secret to building automated alarms that can literally feel their environment. Okay, Section 3, Energy and Action, Powering the System.
Meet Purple Tina Transistor. Do not let her tiny size fool you, Cadet. Tina acts as an electronic switch and a massively powerful amplifier. Just imagine pressing one tiny, really weak button, and suddenly this giant robot wakes up. Well, that's Tina. She takes a super small electrical signal from our sensors and she amplifies it to control a much, much bigger current. She is quite literally the bodyguard of the circuit.
Next up, humming away in bright cyan, we have Kathy Capacitor. You can think of Kathy kind of like a futuristic water tank. She fills up with electrical energy, stores it away safely like a tiny little rechargeable battery, and then releases that burst of energy exactly when the team needs it the most. And finally, flashing in hot pink, meet Benny Buzzer. Benny has a very loud and very important job. When the sensors detect an intruder or a fire, and Tina transistor amplifies that signal, all that energy hits Benny. He instantly converts that electrical energy into sound, making a super loud noise to warn everyone that there's danger.
All right, let's put this into practice. Section 4, the simulation conquering worksheet 3A.
Let's start with questions 3.1 and 3.2. I want you to picture Captain Switch in his awesome electric blue cape. The worksheet is asking about the actual function of a switch and what exactly happens when it's open. Think about it. What does a captain do to that door?
Well, the answer becomes incredibly simple when you visualize our character, right? So your starter answer is, the switch opens and closes the circuit. And for the open state, you'd write an open switch stops the flow of current. The door is open, the gap is there, and the electricity simply cannot jump across. Easy.
Let's fast forward a bit to questions 3.5 and 3.6, which are all about our purple powerhouse, Tina transistor. Now, we already know she can act as an electronic switch, but think back to that giant robot analogy for a second. Do you remember what her hidden superpower is?
Here is the crucial point you're going to want to write down for your worksheet. A transistor can amplify a small current into a larger current. It literally takes the weak little whisper from a sensor and turns it into a giant roar that can trigger Benny Buzzer. It is the ultimate electronic bodyguard for your alarm system.
Almost done. Section 5, mission debrief, memory check.
Let's do a really quick rapid-fire run-through of our complete team roster just to lock this all in. Ready? Captain Switch, blue, on or off. Diana Diode, orange, one way. Lily LED, yellow, blows. Robbie Resistor, red, slows. Tina Transistor, purple, amplifies. Larry LDR, green, light sensor. Theo Thermistor, crimson, heat sensor. Kathy Capacitor, cyan, stores. And Benny Buzzer, kink, sounds. You got this.
Mission accomplished. You now completely understand the vital role every single component plays, and not as boring textbook definitions, but as a dynamic, working team. So here's my final question for you. Now that you know all of their individual superpowers, are you ready to wire them together to build a fully automated, life-saving alarm system in our next mission? Keep asking questions, keep solving problems, and keep building the future. I'll see you in the next explainer, cadets.